Our topic for today are congruences, and we'll be quite busy in this section, so let's start immediately. So definition, and that's a definition that we know from last section, and that is definition. So let A be integers, and then n is in Z plus, and we define A congruent B modulo n if and only if n divides B minus A. We saw examples with 5, 6, it could be done for any number n. Actually, I should be even say n is greater or equal to 2, because no one is interested in relation modulo 1. Modulo 2, that's again somewhat interesting. So, since I have problems with my markers, let me bring the view. So, here are the properties. So, first theorem. So, we have lots of theorems today. 6.4.1. And it says the following. The following are equivalent. This is standard acronym we use in mathematics. So, it's what? A is equivalent with B modulo n. Number 2, B equals A plus Kn for some K in Z. Wow, this marker is great. And A and B have the same remainder. Modulo n, which means what? A mod n, that's how we label the remainders. A mod n is equal B mod. Although, I must admit, this is the official notation we introduced. I'm more used to the notation remainder of A modulo n equals remainder of B modulo n. I think it's a better notation for our class because mod will show up anyway, so it might be a little confusing. All right, so how do we prove this? 1, 2, 2, 3. Very often in mathematics, when we prove that statements are equivalent, we have a chain to use transitivities. It will be like this. 1 implies 2, 2 implies 3, and then 3 implies 1. I don't need to say that to prove that I implies 3 because it's transitivity of implication. So because of that, this is true. So how do I prove that? So 1 implies 2. It's actually exactly by definition A equivalent with B modulo n by definition. So assume A congruent with B modulo n. By definition, that means n divides B minus A, which by definition of divisibility, that means B minus A equals K times n for some K in Z. Solve for B. B equals A plus Kn for some K in Z. That's exactly what 2 says. What about 2 implies 3? What? So now I will assume that B equals A plus Kn. And let us assume that the remainder of A modulo n is R. And then this is just a little review of what we had in that section. What would that mean? That would mean that what? By definition of remainder, A equals Qn plus R, where R is less than or equal less than n. And every number satisfying that is a remainder. But then what? How much is B then? B, it says A plus Kn, so it's Qn plus R plus Kn. I get these two together. Q plus K times n plus R, where R is between 0 and n by definition of a remainder. That's remainder for B as well. So implies by definition that remainder of B B modulo n is R. All right, collect little markers so that I can at least with some colors. So I see we started from remainder A to be R, we got remainder B to be R, so they are equal. And then how do we prove that 3 implies 1? 3 implies 1. What does it say? So assume that the remainder of A modulo n equals remainder of B modulo n equals, I'll call that number R. Nothing special about that R. So what do I know? A equals Qn plus R. B equals Q1 n plus R. And then what? Then I have B minus A. R and R cancel. So I'll get Q1n minus Qn, which is n times Q1 minus Q, so n divides B minus A. Here it is. So we proved that all these three are equivalent. When we have many statements like this in our course, what is the value of these theorems? The value of these theorems is that whenever we establish a fact in one of these three forms, we can just pop up the other two if they are more convenient for our work. So that is really very, very convenient. All right, so that's our first progress. Let's see what else. So we'll need to learn a lot to be able to get what we need. By the way, what? Remark. Because of this, that everybody saw if A is congruent with B modulo n, then B looks like A plus Kn. That's why the class of all B's that are equivalent, so A class, which is class set of all B's, such that A is congruent with B. Very often we say that's A plus KZ. Z stands for MZ. If it's modulo n. Z stands for that arbitrary K. So it says, how do you get class of A? Take A and then add any multiple of n. So NZ means pick any element from Z, multiply by n, and add it up. All right, now we want to do something interesting, and that is we want to establish a little algebra between the class. So let's see how that works. That's what next theorem is telling us. So in that statement, we want the following proposition. Says the following. Number one, if A is congruent with C modulo n, no B, and C is congruent with B modulo n, and then A plus C is congruent with B plus B modulo n. And the second, the same thing for multiplication. Why is this crucial? Because it says that actually this congruence behaves like equal sign. We can just solve the equations and do many things that we are used to do. So proof is fairly easy. What? How do I write the proof? So if A is congruent with B mod n, that means that B equals A plus K. C congruent with D mod n, that means that D is congruent with, D is equal, sorry, C plus L. So I cannot assume that they're the same integer according to the previous theorem. Then what? If I add them up, I'll get B plus D equals A plus C plus k plus la. So that's why these are, so a plus c is congruent with b plus d modulo n, because this is the multiple. Also, if I multiply them, what do I get? B times d is a plus k n c plus ln are 4, and then I get ac plus aln plus kcn plus kln squared. Obviously, this is a multiple of n. This is n times u, so ac plus n times u, because I can factor out n. So ac is congruent with bd modulo n. So it's very easy proof, but it is very important fact, because of this fact, we can actually calculate remainders in a much more efficient way. So here is actually one interesting example, 641. It's really curiosity to see that working, and then also it's very useful. So here it is, we want to calculate. Yes.
Is this for chemistry?
When does your class start?
10:30.
10:30, then probably I should stop here. Thank you.